under the fixed prior distribution is I bits, but its communication cost can be much larger. The goal is to simulate the original protocol within some small statistical distance using as minimum communication as possible. Okay, in this case, we will say that the compressed protocol tau epsilon simulates the original protocol. Yep. You want to produce an alternative? This is just the communication, just the. Right. Yeah. I mean, it's just a worst case measure. So, but you can, yeah. Okay, and we saw that an alternative definition, at least for our purposes, of the interactive compression task can be viewed as follows. We have the protocol tree of pi, which is just defines all the possible intermediate transcripts of the protocol. And the goal of Alice and Bob is to sample a path in this tree. Right? So we have here all the, if the communication of the protocol pi is C, so we have all the binary sequences of length C, let's say. And the goal of Alice and Bob is to sample a path or a leaf of this tree according to the correct distribution, the distribution induced by the protocol pi. Okay? So yesterday we had some useful definitions that will be useful today as well. And so what is this correct distribution? We saw that communication protocols exhibit this special product structure in the sense that the probability of reaching a leaf, of producing the transcript M, decomposes to this nice block structure. So we have the probability on the even nodes, which is on the odd nodes, which is completely determined by Alice's view of the world, times the probability, the product of the probabilities on the even nodes, which is solely determined by Bob's view of the world. Okay, so what are these quantities formally? So remember, we defined this quantity pxw, which is Alice's prior on the world. So it's the probability that in the ith step of the protocol, the next message that will be sent will be little mi, conditioned on Alice's view of the world, which is conditioned on her own input and the history of the protocol being the node w. Right? So for any node of the protocol, whether it is an odd node that she owns or it's a Bob node, this is her best guess for the next message that's going to be sent. And similarly, we define PYW, which is the probability according to Bob's view of the world, which is the probability conditioned on what he observes, his own input and the history of the protocol. Make sense? Okay, and now what is the correct probability? The correct probability combines the odd terms from Bob's view of the world and the even terms from Alice's side of the world, which is exactly this quantity. Okay, so I can define this. It will be a little bit ugly, but P sub x is just the product over all odd nodes in the path M of Pxw, and Pym is the product over all even nodes along the path of Pyw. Any questions? an alternative definition of the interactive compression task is to sample. Another way of rephrasing the interactive compression task is the players just want to sample a transcript or a leaf from the correct distribution, from this distribution. The problem is that Alice only has the first part, but she only has a prior guess on the even nodes. And Bob has the correct second part, the view on the even nodes, but he has only a prior on the odd nodes. Okay, feel free to interrupt if something's not clear. So let's define the correct distribution, pi x sub xy, Alice's view of the world by pi sub x, and Bob's view of the world by pi sub y. Okay, so the intuition is that the players would like to use their own marginal information or prior information in order to produce the correctly distributed path. And the same view applies to yesterday's compression scheme. So yesterday we saw that we saw one approach of producing this correct distribution out of the marginals using a clever usage of public randomness. And today we will see an alternative usage of public randomness to produce that will enable us to produce the same sample using a different approach. Okay, so yesterday we saw that we can always take a communication protocol with information I and communication C, and we can compress it to roughly square root I times C communication. This was BBCR. And today, what I want you to show is the second an incomparable compression result due to Braverman. Which shows that you can take any protocol with information I, communication C, and simulate it using, and let me actually state the formal theorem. If the information of pi is I, communication of pi is C, then we can epsilon simulate pi using 2 to the order I over epsilon or epsilon squared. I forget. Okay, so the appealing feature of this result is that there is absolutely no dependence on the original communication C, which can be arbitrarily long. Therefore, these results are incomparable, right? One will beat the other in different regimes of the parameters. And in particular, last night we concluded with an example on which the BBCR compression performs very poorly, in the sense that the overall, if you remember, the overall information that the protocol revealed was, let's say, 2 bits of information, but the number of mistakes of the BBCR protocol was scaled as root n, the communication. So this was very unfortunate. It seems avoidable. And indeed, I guess the main conceptual difference between these two protocols, as we shall see, is that the BBCR approach attempts to correct each message at a time, right? Even if there's, many errors along the way, the BBCR approach attempts to correct each one at a time. This approach, which we will see today, in some sense tries to correct multiple mistakes at a time. In fact, it will go for a full home run. Alice and Bob will try to correct all of their mistakes in a single shot. So in fact, we will see that you can achieve this communication with only 2 rounds of communication. 1 or 2 rounds. We will see an alternative clever use of public randomness. Okay, so far so good. So our goal is to prove theorem. Okay, so again, what is the setting? Alice has her own prior, Bob has his own prior. The goal is to produce a correctly distributed leaf of the tree. And what I claim is that, so let's try to quantify, once again, what it means that a protocol has low information. What I claim, and we'll formalize this in a second, is that intuitively this means that Alice's prior guess on the even nodes owned by Bob should be close on average to Bob's true distribution on these nodes. And vice versa. The fact that the information is low means that Alice's guess on the odd nodes should be close on average to Bob's true distribution. So let's formalize this fact. So before I do this, so how many are familiar with the connection between KL divergence and mutual information? Okay, okay, so let me do this. If anything is unclear, just feel free to ask. So the assumption is that the information cost of our protocol is I bits. So this is just by definition. Right, this is just the definition. Now, I want to write this in terms of the KL divergence. So we can always write this as the mutual information of the protocol is the expected over the expectation over the inputs in the transcript of the protocol of the log ratio. This is one way to interpret mutual information between the true distribution of the protocol. You know what, let me write this before and then I'll. Is everyone fine with this transition? For those of you who are not familiar with this definition, the way to interpret the mutual information quantity, one way to interpret it is it's the expectation over A, B, and C, you know, X, Y in the transcript of, it's the expected log ratio between so we have the true distribution pi xy, and we have the marginal distribution that Bob has. And the fact that the mutual information is I means that the expected ratio between these histograms, the expected log ratio is I bits.
So pi xi is the distribution over the transcript?
Yeah. So pi xy is the true distribution. Pi sub y is Bob's view of the world, and pi sub x is Alice's view of the world. And what I claim is that the fact that the information cost of the protocol is low, is only I bits, means that the expected ratio between the true distribution and each player's marginal view of the world, each player should have a pretty good estimate in the sense that the log ratio between the true distribution and each player's marginal view in expectation is I bits. Okay? If something's not clear, feel free to.
Distribution, which you take average, x, y, m, is just mu on x, y, and m after for fixed.
Exactly. Yes. Yes. So exactly. So these are distributed according to mu. So I guess the simplest way to do this is to encapsulate all the random variables in our probability space under one distribution, which we can, by abusive notation, think of as the distribution induced by the protocol. But yes, this is.
Don't you have a plus there in the bracket for the two logs?
There is a plus. Okay, so again, remember, what is our goal? We want to formalize the intuition that Alice's guesses for the for the even nodes is close to the true distribution, and vice versa for Bob. But now we can just let's substitute what we actually mean by. We have some additional structure on pi xy. So if we substitute the quantities pi xy, pi x, and pi y with these three definitions, you can see that the first quantity is nothing else but, right, when we take the ratio between pi xy and pi y, the pi y term cancels, right? So we get the ratio exactly what we wanted. We get the ratio between the true distribution and Alice and Bob's guess, right? Let me rewrite this. And vice versa for Bob. Is that right? Sorry. Sorry. That right? So pi xy and pi x.
Aren't you using Q for?
So Q. Okay,
Q
so
is always the prior.
exactly is the wrong prior. That's why it's in red. So yeah, yeah. So okay, so what does this equality mean? It means that on average, px and qy, Bob's estimate, should be close to each other. What?
Because
Yes.
we average over two distribution, so it's better for compression than the false one. So the average is taken over two distributions on M.
What do you mean over two distributions?
No, two distribution on M. So over px of M. So it's positive.
Sure. Okay.
Why is it positive? The log of your log.
Why is this quantity? I'm not saying it's always positive. Right. Well, this is just. I mean, these are two legitimate distributions, right? So you agree that this quantity should be positive, right? Because it's just the KL divergence of
The average.
This is just the average should be positive. But in fact, what I claim, and I will not prove this, is that we can almost use Markov here. Markov applies to non-negative random variables, but the contribution of the negative terms here will be small. All I want you to believe at this point is that we can turn this expected guarantee into a high probability guarantee. So what I'm going to claim without a proof is that before we start defining the compression scheme, let's just ignore all the bad transcripts, all the transcripts M which violate which extremely violate this condition. We can do that by Markov's inequality. So what I claim is that if we define the set of bad transcripts to be all the transcript M such that Px of M I'm not going to use the red one here. Hope you'll forgive me. Okay, so on average, we expect the log ratio between the true distributions and the guesses to be, the log ratio is I, so we expect the actual ratio to be something of the order 2 to the I, right? And I claim that if we just throw away all the transcripts which extremely violate this condition, then the probability under the correct distribution of this bad set is at most epsilon over 10. I think. Okay, might not be exact. Does it make sense?
For every x and y or averaged over x?
No, this is the measure of this set. This is the probability under the correct distribution that these events, that this bad event happens. So all I'm saying is that just take all the transcripts in the world. We know that most of them should be within this 2 to the I gap. Just throw away everything else. Let's just focus on the good transcripts. And by Markov, we lose very little probability. Okay? So, right. But we know that the contribution of the negative terms in the divergence is bounded by some constant, right? So you can, but that's right. It requires a proof. I will not do the proof. Okay?
But this inequality between numbers, it's not for every x and y we have something.
No. No, I'm defining two bad events, and I'm claiming that over the true distribution, these events happen with some small probability, so we might as well just ignore them. Okay, so let me just give you, so far we just did inequalities. We didn't say anything about the actual scheme, which we're going to describe. But I claim that the operational interpretation of this inequality, or of these inequalities, is the following. We're going to formalize this in a second, but what I claim is the following. You can interpret this inequality as saying that the probability, if we draw a random number between 0 and 1. And we know, and suppose we condition, and we know that it fell, this number fell below the distribution Q sub x. Right? This is Alice's guess for Bob's messages. Then one way to interpret this is saying that conditioned on this uniform dart falling under Bob's distribution, it's going to fall under the true distribution, P sub x, with probability at least 2 to the minus I over epsilon. Okay, that's one way. Another way, yet another way to interpret it is that if Bob takes his, if Alice takes her guess Q sub x on the even nodes, and Bob takes his guess Q sub x. If he scales his distribution by a factor of 2 to the I, so this is the histogram of 2 to the I over epsilon times Q of x. So he just scales it. Then this histogram almost entirely contains the true distribution P sub x. Okay? Again, this is just, if this is not helping, I'll move to the, I'm just trying to give you intuition for what's going to happen in the proof. No, it's an average statement. This is saying that the probability under this distribution, the correct distribution, of this bad event happening is small. Okay? Okay, so finally, after all the intuition that was, hopefully it gave us some guidance, but let's move to the formal protocol. So this entire discussion, I claim that it gives rise to the following natural approach. So what the players will do is they will view their infinite shared public random tape as an infinite sequence of darts, basically. So I'm going to describe a rejection sampling procedure that allows the players to use their marginals to sample from the true distribution. So the players will just view their infinitely long random tape as an infinite sequence of three-dimensional darts, which is uniformly distributed in 0, 1, 0, 1, cross. Okay, so what are these darts? Each dart is a uniform sample distributed in the following rectangle, which is the space of all transcripts. So U is just the space of all possible transcripts. So those of you who are familiar with rejection sampling, this is basically what we're doing. So the players will just shoot uniform random darts in this space. Each dart is just has three independent components. Alpha I and beta I are uniform numbers between 0 and 1, and mi is just a uniformly random transcript.
So distribution had nothing to do with any distribution before?
Until now, nothing to do with anything. So far, I described something which is completely uniform, right? And there's a good reason. This is the only manner in which you can exploit public randomness, right? Public randomness has to be independent of the inputs of anything. So the players just view this infinite sequence of darts on this rectangle. And what is their goal? So their goal will be to sample the first dart. You know what? Let me write this here. So the goal of the players will be to sample the first dart that satisfies the following condition, that basically falls under the correct histograms, under the white histogram which Alice has, and the white histogram that Bob has, P sub y. So the goal will be to find and output the first index I star of a dart that satisfies that alpha I star is smaller than P x. So the goal of the players is to find the first index, the first dart, I star, that simultaneously satisfies both of these conditions. And remember, alpha I and beta I are just uniform numbers between 0 and 1, so the geometric interpretation is that they try to find the first dart that simultaneously falls below the curves, the histograms P sub x and P sub y. And I claim, and this is almost by definition, that that this dart has to have exactly the correct distribution. Does everyone see that? So it's clear, right? Alpha I, beta I, and mi were completely independent, right? So the probability that a random dart satisfies this condition is exactly P sub x. the probability that a random dart beta I satisfies this condition is exactly p sub y. So the probability of satisfying both the conditions is just the product, right? These events were independent. And what is this product? It's precisely the distribution pi Okay, any questions? So I claim that we reduced the interactive compression task to identifying the first dart that falls beneath both of the curves.
I guess the picture is still mysterious to me. Where is M in the picture, and what does it?
So
what's the correspondence between the protocol and this picture?
Okay, the players view their public tape as three-dimensional uniform darts, which have three components. Alpha I, beta I are independent numbers between 0 and 1.
Shouldn't you
And
draw the left picture on the bottom?
Right, right. Maybe that's the. So I guess the.
M is
You should.
horizontal, yeah?
Yes, yes. So just take a view only at Bob's view of the world. Bob has the true distribution on odd nodes and the guess Q sub x on even nodes, right? He views this sequence of uniform darts, right? And the player's goal is to try to identify the first dart that simultaneously falls under the white histogram.
What histogram means what? What's the? Can you label the axes for me?
Yeah. So this axis is the axis of the universe of all possible transcripts. So this is M. So every point here, okay, every dart is a uniform number between 0 and 1 for alpha, a uniform number between 0 and 1 for beta, and a completely uniform transcript in 0, 1 to the C. Right.
Should those be on the floor?
Yeah, exactly. This was, I'm sorry, this is not very, so just take a view, just duplicate this image for
Should be on the floor.
Yeah, exactly. So this is the right image. This one should be on the floor and this should be the,
That's fine.
okay. But okay, so whether this picture helps or not, does everyone agree that if the players manage to identify the first transcript, M sub I, the first dart, so the dart is a collection, A, alpha I star, beta I star, M I star. If they manage to find the first dart that simultaneously satisfies both of these conditions, so it falls both under P sub x and under P sub y, then this dart has precisely the correct distribution.
And Alice knows the first condition and Bob knows the second.
Exactly. So neither of them knows this dart, right? But they have some side information that might help them discover this dart, right? Sure.
Isn't it the probability that the dart is correct?
No, I claim that any dart that falls under, that satisfies these conditions, the probability of outputting this dart is exactly this probability.
Okay, so the statement is the probability that the dart satisfies the condition is this expression.
Is exactly the correct, yes, yes, yes,
Okay.
yes. Yes, exactly. Okay? More questions? Okay, so again, Alice can only verify this condition, right? She has P sub x. And Bob can only verify this condition. He only has P sub y. But Alice and Bob do have some guess about this condition, right? Alice does not know P sub y, but she does know Q sub x, which is an estimate, a pretty good estimate on Q sub x, on P sub y. So Alice will use her prior Q sub x to try and guess the darts that satisfy her own condition, that she can check privately, and that satisfy this condition. Right? So the natural approach would be the following. Alice will take all the darts in the board which satisfy her first condition, that she can check, she has this condition, and that satisfy the second condition up to this, fudge factor, right? And then she will take all of these are the potential candidates for being the first dart on Alice's view. And then Alice will just send these candidates to Bob and hope for the best. So does it make sense? So let's try to define this. So Alice and Bob defined the set of potential so just a technicality. What is the probability that a uniform dart actually satisfies this condition?
The average of...
It's just a volume argument, right? The entire volume of this entire rectangle is exactly, alpha and beta I are between 0 and 1, so it's 1 times the space, the size of the universe, so the size of the universe U. Right? So the probability that the volume of a single of the white curves is just 1, it's a distribution, so the probability that any dart satisfies this condition is 1 over U, so it's sufficient, it's enough to consider roughly U such points and not infinitely many points. So I will not formalize this, but this is very easy. So what is Alice's set of potential candidates for being this good dart, this dart that satisfies both conditions? It's the set of indices I that satisfy, again, the correct distribution, the correct condition on her side, right? She can perfectly verify this condition by herself, and they satisfy the second condition up to this factor. Let's say, okay. So this is, from Alice's point of view, this is her best guess. This is the set of potential candidates, potential candidate darts for satisfying this condition.
Which is still significantly larger than the real candidate. So
which is still?
Significantly bigger, the potential.
Right.
Potential.
Right. So she doesn't know the true distribution P sub y. But we know that if she scales her estimate by a factor of 2 to the I roughly, then she's very likely to include all of those examples, because we know that Q sub x and P sub y are not too far apart. They're typically within a ratio of 2 to the I.
So there's this vast thought experiment where they're ignoring almost all the darts, but they just communicate about ones that pass this kind of test? Is that
Exactly. This is exactly what they're trying to do. Yeah, so Bob, let me not define. So Bob will define the same set of candidates. It will be the analogous thing, right? So he doesn't know the first condition, so he will just look for all the darts that that satisfy the second
Even to name these candidates.
Right. That's a good point. So we'll see, we'll resolve this using hashing. So sorry, QX, QY. And she can perfectly verify the second condition, right?
This mystical 8 should also assume be there.
Right. We're taking a slightly larger factor just to, we'll have these bad events that will use, concentration inequalities to argue that these events happen. This 8 is, there's nothing special about it. Okay, I won't do these more. But all I want you to be convinced is that Alice and Bob can privately compute these set of potential candidates using their own marginal information.
So at some stages of the process, Alice thinks that maybe it's a potential candidate, and Bob also, and other sets of stages he thinks. And then the only problem is that they should somehow communicate.
Right, so exactly. So far, no communication, right? Again. Sorry?
They are simulating the whole process.
Exactly.
I mean, they have public randomness for all these darts. They're ignoring most of them.
Right. Right. So, yeah, so we have reduced, what I claim is that we have, okay, so let me not write this formally, but by this claim, we know that with very high probability, with probability, let's say 1 minus, what is it, epsilon over 10. So with probability, 1 minus epsilon over 10. Okay. Probability 1 minus of epsilon. We know that the true dart belongs to this intersection set, right? So what I claim is that we have reduced the interactive compression task essentially to a disjointness problem, right? The players have two sets of potential candidates. They want to find the first one the first element in these sets that occurs in both sets. And really, that's all there's to it. So how I can go on for another 5 minutes and say how exactly they do this. So, from this point, the protocol is essentially clear, right? Alice should just communicate the entire set A to Bob. The problem is that sending an element, a dart I, is very expensive, right? Because sending the actual set A, sending the name of a dart, requires sending the actual transcript, or describing the actual dart takes a lot. But they can resolve this using hashing, right? Instead of communicating the actual names, they can just hash down their elements to a smaller universe. And
maybe you can just mention how many samples they take and what is the size of A.
oh, good. Oh, sorry. That's the most. Yeah. Right. So okay. Good point. So how much communication do they need to find an intersecting element in these sets? We assume it exists, right? So it's comparable to the size of A or B. So the claim is that with high probability, the size of A is less than, I don't know, 2 to the 10 over epsilon, 10I over epsilon. And the same applies to B.
Just to see there is an intersecting element, then they can use Haskell filters or something.
Right, exactly. So I was about to say this in a second. Yeah, let me get back to this point in a second. So all we want is an upper bound on the number of ones, the size of A. And I claim that the size of A is on the order of 2 to the I over epsilon. And the reason, again, it's a volume argument. We took, what is the probability that a uniform dart satisfies both of these conditions? The volume of Px and Q sub x was 1, but we scaled this by a factor of 2 to the I. So Alice takes her estimate, she scales it. This is the scaled version. Right? What is the volume of this scaled up histogram? It's on the order of 2 to the I, right? 2 to the I over epsilon. So the probability that a uniform dart satisfies this, falls under this histogram, is roughly the 2 to the I over the total volume, or the total number of. Yeah, does that make sense? I wasn't exactly formal, but it should be, yeah.
Yeah, but what is the
Where do we use the bound on V epsilon, xy?
Oh, so we use this to say that we know that with high probability, the correct dart will be, we can forget about anything else beyond these sets. Okay, so we know that we can restrict ourselves to finding, we know that with high probability, the right element lies in these sets.
The volume here depends on the communication complexity, right? The volume of the whole space. Because U is the number of bits sent in the first route.
But we divide over U anyway.
Right, so let me try and recover.
So A and B are just sets of indices. Numbers,
yeah,
or it's set of points.
Yeah. Okay, so here's a little bit more formal argument. I claim that it's enough in order to have at least one good dart, it's enough to consider not infinitely many darts, but only something like the size of the universe times log 1 over epsilon darts, roughly. Then with probability, by Chernoff, we can see that with probability 1 minus epsilon, there will be a dart satisfying the correct condition. By claim star, we know that this dart will also be in the intersection of those two candidate sets. And now I claim that if this is the total number of darts we considered, I'm trying to calculate an upper bound on the set A. So what is the expected size of A? What is the expected number of darts satisfying the conditions in Alice's candidate set A? I claim that there are these many uniform darts. Each dart will be good with probability, right? Let's see.
Doesn't that depend on the relationship between I and C?
Two to the I times two to the I. The point is that if you use actual distributions in this kind of experiment, then after U samples, you expect one element.
That we said, yeah.
And now you scale the volume by 2 to the I. So you expect 2 to the I.
Exactly. Sorry, that's the correct, right. We already saw that the probability that a single dart satisfies the correct thing by the volume argument, right? It's just 1 over the volume of the rectangle, which is U, so it's 1 over U.
I mean, the actual, you can only knows the probability that the dart will fall under the curve, right?
Say it again, sorry.
You have to find the probability that the dart falls under the curve, right? And the curve, so
The expected
I claim that the volume or the
compute the volume
Right, and right. So I claim that the volume under the white histograms is 1. The total volume is U, and therefore a uniform dot will satisfy the correct condition with the problem.
The white histogram is 1.
Because it's a distribution. This thing is a distribution.
White histogram is without the true die effect.
Yeah. The white histogram is the true distribution. It's the real distribution. So
No, there are two white actually, which confuse people. So you have a red Q and
okay, let me.
the red is 1, so the red and the other one is 2 to the I. And the other white one only decreases.
Yeah. Okay, let me try again to repeat what Anoop said. So we know that before scaling, before anything, the probability that a random dart falls under the white curves is 1 over the size of the universe. It's 1 over U. So if Alice now takes her estimate and scales it,
You also
so
it's also 1 over U for px times qx.
right, okay. The probability that a random dart falls under px times qx, px times qx is a distribution, so its volume is 1. The probability will be 1.
Never multiply px and qx.
Okay.
px and qy.
Q,
Px
px
and qy.
and q,
Yeah, px and qy.
uh,
Px and qx are both about x.
let me see. So, okay, so
This probability is computed only on the vertical plane, I guess. Without any Q and Qy and Qy. No?
right, so
Sorry, is q the estimate of Alice? So that's
Yeah.
px and qx.
yeah, this is the information that Alice has, and what I want to claim is that if Alice takes, what is the set A? Is all the darts that fall, whose first coordinate fall under the white curve, and whose second coordinate, beta, falls under the 2 to the I scaling of the red histogram.
Not the coordinate, there's a pair. Is that the white curve and
Yeah.
the scale red curve. Yeah.
Yes. Okay, and like
What was the size of the original universe?
the
What was the size of U?
U is just the space of all C-bit transcripts, but we can express everything in terms of U, of just the size of U.
So it's 2 to the C.
Okay, so let me finish this detail during the break. Let me just say, if you believe that the size of A and B with that the size of A is on the order of 2 to the 10i, then I claim we are done, because one way to see it is that if we're trying to compute an intersecting element or to solve the disjointness problem on sets of size k, we can always do this using order k bits. Regardless if those elements live in a huge universe. This is just...
Don't you need to add the log of the size of the universe condition?
No, so that's a more clever protocol that... So basically what the players will do, right, the problem is that the number of ones, the number of true elements is small compared to the universe, which is huge. The universe is all possible transcript, but the players can intuitively hash those inputs into a smaller universe. But anyway. Right. So there is you can use hashing and solve this using, okay, instead of Alice sending each and every element here, she can just send hashes, like order I hashes of each element. That will be slightly more expensive, but this will suffice. So it's a minor detail. I just wanted, the heart of the proof is showing that we reduce the interactive sampling problem to essentially to a disjointness problem. Each player has a list of 2 to the I potential candidates, and the goal is to find the first, any element that occurs in both sets. Okay, and we know that not any element. Sorry. Once Bob receives the element, he will check for the first one that basically satisfies the correct that satisfies what is this? So
probably both should cancel the set at the same, check intersection again.
No.
Check whether the first one will
No,
stick to this place.
I claim that Alice will send these elements or hashes of these elements, and Bob will just take the first element that occurs in his set. And that's it. We know that this first element is likely to satisfy the correct condition.
And the size of the elements doesn't matter because we don't restrict public randomness and we can compute large.
Yeah, on the public tape, we might as well write the infinite sequence, but for actually communicating the set, absorbing another tiny error, we can just use hashing. So that finishes the protocol. So I'll get back to you with the small calculation after the break and we can continue.